Right.
Can you
So
check?
welcome back, everyone. The second lecture today morning is by Anupam Singh from ISER Pune, and he will speak on Z classes in groups. Anupam, please start your lecture.
Thank you, Professor Verma. I'm here in the same auditorium. It's just that I'm facing other way around. So I'll talk about this topic, Z classes in groups. This topic was, it's kind of very interesting that I'm giving a talk on this topic here, because this topic was introduced to many of us by Professor Kulkarni when he gave a series of lectures in HRI when I was a PhD student. I think it was around 2003 or something like that. It was a semester-long lectures, and it was quite interesting and motivating, and it motivated many of us to take up this topic. So I'm going to share some of the work done in this direction by many people. So this is going to be roughly a survey talk, and there is another talk scheduled in the evening by Vikas. He will also talk about some aspects of this subject. Okay. So let's begin with talking about what a conjugacy class means. This is familiar to almost everyone, even students at undergrad level. Suppose I have a group G, and if I take two elements, G1 and G2 in this group G, we say that G1 and G2 are conjugate if there is some element T in G, such that T G1, T inverse is G2. Right. So we also check that if I define this condition, this equation, then it's an equivalence relation on the set G, and the equivalence classes are called conjugacy classes, right? And if you have studied finite group representation theory, you know that this becomes quite important there, because for a finite group G, the number of conjugacy classes is same as the number of non-equivalent irreducible complex representations. So if you want to study representation theory, it becomes quite useful if you know something about conjugacy classes, the number, etc., and so on. So it plays a quite important role in representation theory and vice versa. So understanding conjugacy classes is, of course, one of the central problems in group theory and representation theory. What do we mean by G classes? I will call it G classes, as Professor Kulkarni likes to call it, and we have got used to calling it G classes. So two elements, G1 and G2 in G, they are supposed to be G equivalent or G conjugate if they're centralizers or conjugate subgroups within the group G. Yeah. Why I'm emphasizing on within, I will you'll see that it plays some role. That is, if there exists a T in G such that centralizer of G1 in G, it's conjugated by T to centralizer of G2 in G. It's quite easy to verify that G conjugacy is also an equivalence relation on G, and it represents the conjugacy classes of centralizer subgroups of G. So if I take centralizer of all elements, and I think of the conjugacy of those subgroups, that will be basically giving me this. So these equivalence classes are called the G classes or the centralizer classes. All right. So what is the relation between G classes and conjugacy classes? If I take two elements which are conjugate, one can easily verify that they're also Z conjugate or G conjugate. The conjugating element, the element which conjugates one to the other, that itself will also work for the centralizer subgroup. However, the converse need not be true. So of course, these two are kind of different notions. In some sense, G classes is much weaker, and easy example to see that is abelian groups. If we look at abelian groups, conjugacy classes are going to be like each element is a conjugacy class, whereas the centralizer, since centralizer of every element is whole of the group, there is exactly only one G class. right? So basically, if you look at G classes, it forgets abelian groups in some sense. G classes are union of conjugacy classes because of the comment, first comment here. The notion of G classes was introduced to, as I said, to many of us by Ravi Kulkarni, and there are a couple of papers in 2007-8 where he talks about this for GL and so on. This notion is different from asking if the centralizers are isomorphic as an abstract group, and that could also give rise to an equivalence classes, but that's not what we are talking about here. We want the centralizers to be conjugate within the group, not abstractly isomorphic. I think I have some easy example to see that. So first example we can look at is any abelian group. If I look at an abelian group, as I said, there are as many conjugacy classes as the number of elements. However, there is only one class, right? So this tells you that why this is interesting notion. Thus, we focus on studying non-abelian groups. So now, whatever I will talk about, usually I will assume non-abelian groups. If I look at the very easy example like symmetric group S3 and S4, one can try to compute this easily, and you will see that in these two cases, the G classes turn out to be the same as conjugacy classes. But if I look at the next one, S5, and if I look at the element 1, 2, 3, 4, 5, and only 1, 2, 3, the centralizers of this will turn out to be kind of same, because you know the 4, 5 also centralizes the element 1, 2, 3. So if you look at the centralizer, it will be generated by 1, 2, 3 and the element 4, 5. That will happen for the both of these elements. So it's not quite same, and these two elements are not conjugate, so it's not quite same. That conjugacy class is same as G classes for the group S5. And in general, it turns out to be that like, you know, this kind of things are the only exception. I'll talk about it later, the results which I have proved for this. Yeah, the precise result for symmetric group is an alternative group is in the paper by Bhunyakor and myself. If I look at another example, easy example of Q8, and the element here is plus minus 1 are central. So, but if I look at the element I, J, K, the centralizers of this will turn out to be the subgroup generated by the element. So if I look at the centralizer of I, it's of order 4, plus minus I and plus minus 1. And if I similarly look at the centralizer of J, it's going to be plus minus J, plus minus 1. And these are abstractly isomorphic, but they're not conjugate within the group QA. So this is an example to keep in mind that the notion of Z class or G class, what we are defined here, we are looking at if the centralizers are conjugate within the group. Yeah? Otherwise, it will be slightly different problem. Let's talk about this question for algebraic groups. That's what I am going to mention here. Let's quickly recall. I mean, I'm not going to give an exposition, but just for the sake of completeness, just recall the definition of algebraic group. So we consider a linear algebraic group defined over base field K. What does that mean? So an algebraic group G is supposed to be defined over algebraically closed field. So I begin with capital K, an algebraically closed field. An algebraic group G is an affine variety which is defined over capital K with a group structure where the group structure maps, the group operation maps, namely multiplication and inversion. They are supposed to be morphisms of variety. Okay, and then there is a notion of the group G defined over base field small k. So I'm assuming I'm beginning with the base field small k, and roughly this means that an algebraic group G is said to be defined over base field k if the coordinate ring k bar G is defined over k. Yeah, in the sense of algebra, the k points of G will be denoting as GK, right? The typical example you can keep in mind is, for example, GLN, orthogonal group, symplectic group, or upper triangular matrices, These are the typical example of groups, algebraic groups, which we want to look at here. And if I want to look at it over any field small k, I can just, for example, if I'm looking at GLN capital K is the algebraic group. G, it's an affine variety defined over capital K. And its small k points will actually turn out to be here. It's a GLN small k. So it's quite easy to see for this example. But in general, it might look slightly tricky for one to imagine. Okay, so what kind of question we are interested in here for this this group, algebraic group? Let's explore the question of conjugacy classes and G classes for GK. So I'll be interested in understanding conjugacy classes and G classes, not just for the group G or algebraically closed field, but over small k also. Remember, small k could be any field on which G is defined. Yeah. So note that the conjugating elements are supposed to be over the base field in the field in the set GK, you can say. When we consider the G classes, we take the centralizer subgroup and its k point under the conjugation axiom. Yeah, just to clarify, when I say G classes, we'll be looking at again conjugacy over GK for the k points, small k points. For example, if I want to look at regular semisimple elements, so in GLN, for example, the regular semisimple would be a diagonal element which has all distinct elements on the diagonal. Right, so that's an example of regular semisimple element. And if I look at its centralizer, you will see that the centralizer is diagonal subgroup. So in general, one can generalize that idea. It's supposed to be a semisimple with minimal dimension centralizer. So when we consider regular semisimple element, the centralizer would turn out to be maximal torus, right? And if I'm looking at, if you've done a little bit of algebraic groups, you would know that look at algebraic closed field, this maximal tori would be conjugate. However, for example, reductive group, there will be conjugate. Whereas if I look at over some field, smaller field, small k, over maybe rational field or over finite field, there are like not all maximal tori are conjugate, right? So that's the idea here to understand some of these concepts. All right, and here are some examples. Let's say some easy example again to keep in mind. So if I look at the group GL2 over C complex numbers, that means I'm looking at GL2 or algebraically closed field. Then if you look at G classes, there are only going to be 3 G classes. One is represented by entity, and another by regular semisimple element, and another by unipotent elements. So there are 3 G classes here. This can be also computed easily. I mean, one way to compute is that first write down the conjugacy classes, and then you see what the centralizer is and check whether they're conjugate or not. And in this case, it's quite easy. Once you write down the, let's say, Jordan canonical form for elements, and you can compute centralizers, and you'll see that they're different here. They're non-isomorphic, in fact, in this case also. However, there are infinitely many conjugacy classes, right? Because, for example, you can take semi-simple elements, that means diagonal elements, and you'll see that they are different conjugacy classes. So there are infinitely many conjugacy classes here, but there are just 3 G classes, right? What if I look at GL2 over real or finite field? Of course, if I look at over finite field, FQ, the group itself is finite. So there will be finitely many conjugacy classes as well as finitely many G classes. So the question is not so interesting here if I want to see finiteness. But over GL2R, again, you can see that there will be finitely many G classes. Yeah. However, if I look at the GL2 over rationals, there are infinitely many G classes. This is an interesting exercise for students to do this. Because there are degree 2 field extensions which are non-isomorphic, and somehow you can use that to show that those can be captured by, they will give rise to some kind of maximal tori, and they can be captured by centralizer of regular semi-simple elements. And so you see some kind of phenomena here. If I change field If I look at complex, if you can look at real or FQ, GL2 has finitely many G classes, even though it can have infinitely many conjugacy classes. But over GL2Q, that's not quite so. So one can ask this question, when do we have finitely many G classes over small k? So we'll come to that. Before that, is it true that if I look at algebraically closed field, more broadly algebraic groups of finitely many G classes, right? So there is an answer to this question in Steinberg's work for reductive groups. So let me mention that here. So if I take a reductive group G, a connected reductive group, which is defined over algebraically closed field K of good characteristic, which means you can just avoid characteristic 2, 3, and maybe 5. Then it turns out the number of conjugacy classes of centralizers, which is basically to say the number of G classes, that is finite. This work is kind of very interesting. It relies on understanding unipotent conjugacy classes by Richardson and Lustig. The proof of this theorem is just kind of one page if one knows the work of Richardson and Lustig for unipotence. So yeah, so let me move to this question. Over what field one can say that there are finitely many G classes, right? Now I want to study over base field, right? So this the answer by Steinberg, the theorem of Steinberg says that over algebraically closed field for connected reductive groups, I have finitely many classes, but can I do it over some other field also? So for that, we'll work with what is called fields of type F. We consider a perfect field K, which has only finitely many extensions up to isomorphism, of any given degree. Such fields are called fields of type F. This is by Borel and Say. It's also it's a paper of Borel and Say, but it's also part of this book Galois cohomology by Say, the last chapter. Examples of this kind of field, fields of type F. You can take algebraically closed field, real numbers, finite field, periodic field, CT. This kind of fields are basically fields of type F. But if I look at the rational numbers, that's not field of type F, because you can easily show that when there are degree 2 extensions which are infinitely many. So the fields of type F have some interesting arithmetic property which plays a role. For example, you can also look at quadratic forms. There are going to be finitely many quadratic forms over fields of type F. So here is the question. So if I take a linear algebraic group defined over field K, and suppose K is of type F, the question is, does GK have finitely many G classes? So of course, if K is algebraically closed and G is reductive, it's answered by Steinberg in some sense, right? So let's see what we can do. So here are some results which were proved kind of case by case. I'll mention them. When Professor Kulkarni was talking about G classes in 2003-4 to us, Ronnie Gurej was looking at this for quaternion algebras and matrix algebras or division algebras. It's in its PhD thesis in 2006. Krishnendu and Kulkarni have in 2014, they proved this, that orthogonal groups and symplectic groups, the number of G classes is finite, where the B for orthogonal represents symmetric bilinear form, and for symplectic it represents of course skew symmetric bilinear form. So if this is true, or if I look at the fields of type F. Sushil Bhunia and myself, we looked at unitary groups in 2019, and we proved the same result, similar result, that there is finitely many G classes. Anirban Bose, in his PhD thesis, he calculated what is called genus number for simply connected simple algebraic group for algebraically closed fields. So he computed some kind of this precisely the numbers here, because there are finitely many, that is already kind of known, but actually counting the numbers. So finally the general results we proved. So this is work of Shripad Garge and myself. We solved this problem for reductive groups with some mild assumptions on the group and the base field. These assumptions are required because we wanted to do Galois cohomology, and the kind of subgroups we wanted to look at, they have to be smooth. So those kind of assumptions were required. For example, one has to avoid some small fields, characteristic 2 and 3 and 5, and something divided in order of n plus 1 and so on. So the theorem is this, that if I have a nice group, reductive algebraic group defined over a field K of type F, then the group GK has finitely many G classes. And kind of the idea of the proof is one has to look at normalizer of centralizer of an element, and somehow one has to show that it has only finitely many forms of a base field if I look at this kind of field. However, so this is for reductive group. What can one say about some other in general algebraic groups? So I'll come to that later and show that it may not be true in general. In fact, so maybe this is kind of best possible result looking at reductive algebraic groups. Okay, so I'll slightly jump to slightly different kind of topic. I mean, again, related to this. So motivation from geometry. So what I'm going to do is that define what is called orbit types. So if I look at any Lie group and look at any X G space, a manifold or something, I can look at orbits. So the X is a G space, meaning G is acting on the on this space X. So if I look at two orbits, Gx and Gy, we say that they have the same orbit type if the stabilizers are conjugate in G, right? So for example, if I look at X to be G itself, then it will give rise to G classes, right? We'll come to that. So if I look at two elements X and Y in X, which have same orbit types, that will mean that Gx and Gy are conjugate in G. And you can see that this will give rise to kind of equivalence relation on capital X. And yeah, the main question is to determine the orbit types or representative of the orbit types. Okay, so there was some conjecture about this by Montgomery. Again, finiteness question was asked. So Montgomery conjectured that if G is a compact Lie group acting on a compact manifold, then it has only finitely. And this conjecture was proved by Floyd, 1957, proved this conjecture positively for a torus group acting on compact orientable manifold, and the full general conjecture was proved by Mostow same year. So if you use this, one can say that if I'm looking at compact group, then there are only finitely many G classes. Anyone has any question? Okay, so an example to keep in mind here is that if I can look at the group SON acting on the sphere n-1 sphere, Sn minus 1, and the action is defined by G comma X going to G of X. And you can see that the isotropy groups are conjugate to the subgroup SON minus 1. This is kind of a classic example to keep in mind for the situation. So if I look at compact group acting on itself, and that will give rise to G classes inside the compact group. And one can ask the question, again, what can we say? Can we count the number and can we classify exactly which are G classes and so on? So G classes are a special case when G acts on itself by conjugation. Thus it follows that the number of G classes is finite for a compact Lie group. And the question is to precisely tell the number of G classes. When I was a PhD student, Professor Kulkarni was giving these lectures on G classes. I was working with the groups of type G2 at that time. For my PhD thesis, I tried to look at real and strongly real elements in the group type G2. So he also told me to compute the G classes for this group, at least over compact G2 or R. And I did that and showed that there are finitely many. In fact, there is exactly six classes. Later, Anirban Bose worked on this for his PhD thesis and precisely computed the number of G classes for compact simple Lie groups of type A and B and C and D and F4. They are all done case by case, and precise number is there in this paper. So it still leaves out some groups of typing basically here. It would be nice to complete this computation for the remaining simple groups, basically the typing here. So there is a lot more work done by Krishnendu Gangopadhyay and Ravi Kulkarni and their students. I'm mentioning here some of them, not all of them. So in 2009, they studied G classes for the group PUN1, the isometric group of the real hyperbolic space. Explicit counting of G classes in UN(1), the isometric group of complex hyperbolic space is due to Chao and Gangopadhyay, 2011. Gangopadhyay in 2013 gave an explicit counting of G classes in SPN1, also in SPN, the isometric group of the quaternionic hyperbolic spaces. There are many more results, as I said, by their students and postdocs and so on. So towards the end, I'm going to just talk about some more results especially for other groups like finite groups and solvable groups, very briefly. And as I said, Vikas might talk about some of these things later in the evening today. So as I was telling earlier, that if I look at an algebraic group, we showed that for reductive algebraic groups who are fields of type F, there are finitely many G classes, right? And now the question is that if I take fields of type F, can we show that even for solvable groups or more general algebraic groups, there is some kind of finiteness? And what it turns out that is not true, highly not true in some sense. So if you look at the upper triangular matrix group, we can denote it by B and K. This is for, the notation is thinking of it as a Borel inside GLN. So look at the upper triangular matrices. If I try to compute G classes, it turns out that up to n is less than equal to 5, it is finite. But as soon as we go n equal to 6, and the field is infinite, it is always infinite. This was proved by Bhunia in the paper 2020, that number of G classes in B and K is infinite whenever the field K is infinite for any n greater than equal to 6. And so this doesn't depend on putting, you can't, even if you put some assumption on K, it plays no role here. So that is kind of very, very different from what we got for reductive algebraic groups. So what are the results known for finite groups, some other finite groups? There's a lot of work done by Rahul Kitture and Vikas Yadav. And they proved that if G and H are isoclinic group, then the number of G classes in G is equal to the number of G classes in H. Isoclinic means basically forgetting abelian group. So that is quite apt in beginning, as we saw, that for abelian groups, the G classes is just 1. So G classes basically doesn't distinguish between different abelian groups. So it is indeed true that if two groups are isoclinic, the number of G classes is the same. They also obtained several results, especially for P groups. And I have not mentioned here, but there are several results here. Sushil Bhunia and Dilpreet Kaur and myself, we looked at symmetric group and alternating group because we did not find precise result for these groups. So we actually explicitly computed for symmetric group and alternating group, and we proved that there are very few exceptions. So it depends on, of course, one has to look at conjugacy classes first, and then try to, as we know, the conjugacy classes here are related to partitions. So can one give some condition on partitions which will determine G classes? And it turns out that there are very few exceptions. It's basically just saying that you had to avoid 1 to power 2 and 2 to power 1 for symmetric group. And that's the only exception in some sense here. And as I know, the work is in progress for other finite while groups by Dilpreet Kaur and Uday Bhaskar Sharma. I think they have computed already for classical while groups, and they are trying to compute for exceptional while group using gap maybe. And soon probably this work will complete. So my talk is based on this survey article by Sushil Bhuni and myself, which appeared in Journal of Pure and Applied Maths. One can look at this article for more, and I think I will finish here. Thank you.
It was that ICTS program.
Yes, this is ICTS proceeding which has appeared here. Yeah, so now it has appeared. Yeah. So this was basically proceeding of the conference which happened in ICTS. Yeah, yeah. So if there are any
Thank
questions.
Anupam for his very nice survey talk. Are there any questions? Yes, please.
So, this is studying of systems to groups over. For example, you take SLI and there are some inside. Are there any classes?
Okay, so this is a very good question. So maybe I'll just tell the question again here, which Siddharth asked here. So the question, as I understand, is roughly this: if I look at a group G and subgroup H, or you can think of general situation H sitting inside G, the centralizers inside H, and thinking of centralizer in G, they can get fused, right? And in general, there is no fusion system. The question is that how G classes behave in that. As far as I know, there is no systematic study. What we were looking at for algebraic groups is, you can say that we were trying to vary the field. So, but type of group was fixed. So obviously there will be it will be slightly tricky because centralizers don't behave very well if I think of subgroup. So I don't know really the answer, but in particular examples, maybe one can have a nice answer. Depends on that.
I have only one comment. So I think your thesis problem. Your thesis problem, I think that was also real element problem.
So for my thesis, I worked with real and strongly real elements.
That was suggested by in a lecture.
We were looking at those kind of questions. I think I had started a little earlier with that question. Yeah. But initially, I was only interested in understanding real classes. But then after discussing with Professor Kulkarni and others, it turned out that I should try to classify real in terms of strongly real, which is what I focused later on.
Yeah, so Anupam's thesis was about real elements and my thesis was about three classes. But after we became professional mathematicians, we interchanged our forms.
Yeah, that is interesting. Yeah. So I was suggested about understanding real classes because real classes kind of classify what you call representations which are self-dual. So the question was motivated from representation theory. If you want to classify, if you want to get the number of self-dual representations, one has to look at real characters, and in turn, it turns out that one has to look at the real conjugacy classes. I was interested in classifying which groups or how many real classes are there. But just trying to classify real classes was a little tricky. So it turned out that I should look at the elements in terms of product of involution, which is notion of strongly real classes. This worked out very well for groups of D type, if you look at algebraic groups and things like that. But in finite group theory, more general, it's not really very, there is no really nice answer. But I think recent work of I think there is now this kind of thing proved already, that number for groups of D type is same for the two of these. Yeah. Yeah, so there is also associated problem even for G classes here, that can one count this, and I have not put that slide here. In the survey article, there is a section. So if you are thinking, for example, for groups of Lie type or over finite field or something, one can try to count the number of G classes and try to get a generating function or something. So we have a generating function for unitary group when we were working for that or finite field, and there was some interesting pattern for fields of type F. The splitting from complex to real and finite field, it reflects how many field extensions of a particular degree are there. So that was, but I mean, we have not carried forward that kind of thing. I think it should be done for other groups, and we have posed this question, I think, in this survey.
The original geometric motivation was to compute to see the types of geometrical transformations of isometries of the well-known geometries. And this is a mathematically vague question. We just say, what are the types? And in order to see besides the Euclidean geometry, there are the other spherical geometries and hyperbolic geometries. And those groups tend to be reductive or whatever. And there the types roughly correspond to the Z classes correspond to types. And Z classes is a much more precise formulation than this vague question of geometrical types.
Right.
It is right. I think you should see something about that. The geometries are parameterized by the just integers many times.
Right.
And then you get these nice generating functions.
Yes. Mm-hmm.
And those generating functions, they are not these modular functions, unfortunately,
Right.
where the modular functions are much more structured. But these other generating functions, I think one should see what they are.
Yeah. Interestingly, the word types is used in representation theory by Greenberg. No, in Green, basically, who did the representation theory of GL and Q. So he also called it types. And the types definition is same as basically G class definition there.
Yeah. No, I was just interested in simple case symmetric group of the sphere, symmetric group of the hyperbolic plane.
Right.
So, yeah. So as you go from geometry to algebra, you go from thermo yoga to nano yoga. Yeah.
Okay, are there further questions? If not, let us thank Anupam for his very interesting talk.
Thank you. Thank you, everyone. Thank you for attending the talk.